Hey, everybody, welcome back. We are doing part 2 for chapter 4. This is the addition rule. And if you're wondering, there is a multiplication rule. It does exist. We're going to start by talking about the complement rule. Notice this is spelled complement, so this is not like saying you look very nice today. This is the opposite. Basically, what we're saying is when I know something, if I have a group of dogs and 30% of them are male, we can do the complement and go, you know what, if 30% of them are male dogs, then that means 70% of them are female dogs. And so that's kind of how this works. That's where this 1 comes from here. That's the 100% when we add up two complements of one another. We should always get 100%. Typically, we're going to write it as 1 minus. That's going to be our sort of more normal way of doing that. So if I know that P of E is 0.29, then P of not E, which is what this notation is with the line above it, is going to be 1 minus P of E, or 1 minus 0.29. Giving me 0.71. So there is the complement. Now, there's many uses for the complement, and we will use it a couple of different ways here. So we have for our next example, we have a bag of candy. And there are 4 flavors. There's lemon, grape, cherry, and blueberry. In fact, I want to know what the total is. That's going to be 80 plus 35 plus 25 plus 20. That's going to be my denominator here. So 80 plus 35 plus 25 plus 20 is 160. Now, there's 2 ways that we can say, if the candy was chosen at random, what is the probability that it's not blueberry? I'm going to do this 2 different ways. The first way is probably the way that you're thinking of. How many of them are not blueberry? Well, that's going to be the 80 plus the 35 plus the 25 out of the 160. Which gives us the 80 plus the 35 plus the 25. So 140 over 160. And that's going to reduce, oops, so 140 divided by 160 is going to give us 7 over 8. Or 0.875. And those are our answers. So they didn't specify that they wanted a fraction or decimal, so we put both. Now, the other way to do this is using the complement. The probability of not blue is going to be the complement of blueberry. Probability of randomly selecting blueberry. All right, well, that means this is going to be 1 minus. There are 20 blueberries. And you can see we end up with 7/8 again. So you can see we're getting the same answer either way. Now, you might be thinking to yourself that maybe the first way was easier, or that was the first way that you were thinking about it, which is fine for a simple one like this. But eventually, we're going to get to a point where our only option, not only, by far the easiest option is to use the complement. Okay, our next example, this is the data represents the live multiple delivery births, particularly for women between the ages of 15 and 54 years. Now, I like this because we can clearly see the vast majority are in the middle here. And we all know people that have had children. They tend to be in the ages between the 20 to 40. Typically, we all know some that were younger and some that are older than that, but this is the typical. So the thing that I need first is the total. And when I add all these up, 92 plus 515 plus 1623 plus 2, 8, 2, 4, plus 1, 8, 5, 2, plus 3, 7, 3, plus 1, 15. 7, 3, 9, 4, yeah. Now that's going to be my denominator for all four of these parts here. So start with part A. So it says a randomly selected woman between the ages of 15 and 54 years having multiple births is randomly selected, determine the probabilities, and they want it as a fraction. So the mother's between 30 to 39 years old. So the probability between 30 to 39 years old. Now, I can see 30 to 39 is here and here. So what I'm going to end up with is 2824 plus 1852 over the total of 7394. 2824 plus 1852 gives me 4676 out of the 7394. Now that reduces, but I'm not going to bother reducing. I'm just going to leave it as is. If your teacher specifically wants you to reduce it, then you'll need to reduce. So just keep an eye out for that. Part B. Part B says the mother is not 30 to 39 years old. I'm going to use the complement rule on this one. So not 30 to 39 is going to be 1 minus the probability of 30 to 39. Minus 4676 or 7394. 7394 over 7394. Got to get a common denominator. That's my 1 that I just wrote. Minus 4676. 7394 minus 4694. Oops, that's not right. 4676. 4676 gives me 2718 out of 7394. Once again, this does reduce, but I'm going to leave it in unreduced form for now. All right, part C. Mother, probably that the mother is less than 45 years. Now I could add all those up, or I'm going to do the complement. So this would be 1 minus, and how many are 45 and up? That's 115 over 7394. And that's going to be much nicer for me. 7394. Again, getting a common denominator with the 1 there. So 7394 minus 115 is going to be 7279. In part D, mother is at least 20 years old. And I'm going to say that is the complement of being less than 20 years old. And we can see that is just 1 minus 92 over 7394. Again, getting a common denominator with the 1. Again, that will reduce, but I'm going to leave it unreduced for now. So it's not too bad. And that complement really does save us a little bit of work in this case. And a little bit later, it's going to save us quite a bit of work, actually. All right, let's move on to some ALEKS examples. In a certain online computer game, there are 560 players on the green team and 1,000 players total in the game. The game randomly chooses a player to receive a bonus. Let event A and event B be as follows. The player in the game chooses is on the green team. Okay. And B is the player the game chooses is not on the green team. So that's going to be the complement. So probability of A is going to be 560 out of 1,000. And for part B, that is not green team, this is going to be 1 minus probability of A. So a 44% chance of not being on the green team. Not too bad. Disjoint or mutually exclusive events. These are two events that are disjoint or mutually exclusive if they have no outcomes in common. Then the addition rule is the probability of E or F. We just add up the two probabilities together. And we have a few examples here. So we have a 52 card deck, and they want it as a simplified fraction. What's the probability of randomly drawing a king? Well, how many kings are in the deck of cards? There's 4 kings out of the 52. That's going to reduce to 1 over 13. Part B, probability of drawing the 5. Well, there are, again, 4 5s out of the 52. Now, part C says draw a king or a 5. Well, there are no cards that are both a king and a 5 at the same time. So this is just going to be the probability king plus the probability of drawing a 5. There's no overlap at all. Now, this doesn't happen all that often. There's often overlap on things. That brings us to our general addition rule. This is a big one. We will use this numerous times, actually. So what if they're not disjoint? What if they do have something to do with each other? The probability of E or F, we take the probability of E plus probability of F. But the problem is, if there's overlap, then we've added that 2 times. So we have to subtract one of those out. And let's do this by example. So a tile is selected from 7 tiles, each labeled with a different letter from the first 7 letters of the alphabet. I'm going to assume that this is the English alphabet. So A, B, C, D, E, F, and G make up the first 7 letters of our alphabet. Event X, the letter selected comes before E. Now let's highlight that. That is going to be these here. Event Y is the letter selected is found in the word face. Now I'm going to rearrange the letters and put them in alphabetical order. All right. So we're going to go to part A. It says event X or Y. Now the or is the key here. Event X or Y means that we want to be all inclusive. This is going to be A, B, C, D, E, and F. Now you'll notice that there's some overlap between event X and event Y. The or situation, it doesn't matter. We're just going to count it once. Now event and Y, here we only want the overlap. They both have an A and they both have a C. So there's only two letters where there's overlap. And part C says the complement of the event X. Okay, event X is all the letters before E, so the complement of X is going to be E and on. So these are exactly the opposites. All right, moving on. If a 12-sided die is rolled resulting in a sample space of 1 through 12. Event F is 2, 4, 6, 8, 10. Event G is 8, 9, 10, 11, and 12. So for part A, it says list the outcomes of events F and G. So this is the all-inclusive one. I'm sorry, this is the and. This is the exclusive one. So F and G is only going to be the 8 and the 10 that they both share. So there are a total number of 2 numbers in this set here. Part B, now we're going to list F or G. So we want the events all of F and including all of the events in G. So this is going to be 2, 4, 6, 8, 9, 10, 11, 12. So this is the all-inclusive one. All right. Part C. Find the probability of event F and G. Well, there's only 2 in event F and G. By the way, I didn't put over here. I should mark that there are a total of 8 numbers of events F or event G. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Part C. So F and G, there are 2 elements out of the 12. And that reduces for us. Did they tell us to leave as a fraction? I don't think they say. They do not. There we are. You could even put 2 over 12. You don't even have to reduce it. Part D. Find the probability of event F. No problem. There's only 5 out of the 12 there. And E. Probability of event G happening. Again, there are 5 elements in G as well. Parts F and part G should yield the same answer. So part F. It says find probability of F or of G by counting. So I'm going to go back to part B. It looks like there's a total of 8 out of the 12 that are in event F or in event G, which reduces to 2/3. And I'm just going to leave that as a reduced fraction. And now we're going to use the general addition rule for part G. Well, this is going to be probability of event F plus the probability of event G minus the probability of event F and G. All right. So this is going to give us 5 over 12 plus 5 over 12 minus 2 over 12. That's from part C. And that gives us 8 over 12, which again reduces to 2/3, as we would expect. All right, let's keep going with this general rule of addition. Here we have what's called a contingency table. The way we would read this is the total number of freshmen is 97. The total number of freshmen that are neutral about the student government, which is what this scenario is 24. And you can see those totals at the other end as well. All right, let's do this. My denominator is going to be the 371. So first off, what is the probability that he or she is satisfied with student government? So probability of satisfied, my denominator is 371. And how many total students are satisfied? That's 236. And I'm looking at it asks us to round this to 3 decimal places. So 236 divided by 371. 0.636. Part B. What is the probability that he or she is a junior? Part B. How many juniors are there total? There's 89 juniors. So we're looking at, let's off to 3 decimal places. That's going to be 0.240 if I round that up correctly. Part C. Oop. Part C. What is the probability that he or she is satisfied and a junior? Satisfied and a junior. How many satisfied juniors are there? There are 65. Just to make sure you know where I'm getting my number from, the total number of satisfied juniors is right there, the 65. All right, so that's going to give us 65 divided by 371. .175 is what I'm getting. Part D. What is the probability that he or she is satisfied or a junior using the general addition rule? Okay, so probability is satisfied or a junior. So this is going to be the probability of satisfied. This probability being a junior. Minus the probability of satisfied and a junior. All right, so this is going to give us our 236. This is from part A. 236 out of 371 plus part B, 89 out of 371 minus satisfied and a junior, which is part C, which is the 65 over 371. 236 plus 89 plus minus, pardon me, minus 65 gives us 260. getting that 0.701. And part E, find the probability that he or she is a freshman and not satisfied. So probability freshman and not satisfied. So unsatisfied freshmen, there are 15, it looks like. .040 is what I'm getting. All right. Let's do some ALEKS problems. We have a deck of 8 cards numbered 1 through 8. Some are gray and some are white. The cards numbered 1, 2, 3, 4, 6, 7, 8 are gray, and the card numbered 5 is white. The card is drawn at random. So let's talk about event X. Event X is the event that the card drawn is gray. All right, so we have here, 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 and here. That is 7 out of the 8 are gray. Not X, there's only 1 out of the 8. Now, 1 minus probability of not X, that's 1/8, is 7/8. And we'll note for part C, it says select the answer that makes the sentence true. 1 minus probability of not X is the same as P of X. P of X is going to be your option that you'll choose there. All right, last one for the video. Yep. All right, Fran the Fearless has a well-known act at a local zoo. As part of the act, Fran handles scary animals that she picks at random out of a box of terror. The following animals are in the box: 9 poisonous snakes, 7 non-poisonous snakes, 8 poisonous spiders, and 5 non-poisonous spiders. What is the probability that the animal Fran picks is poisonous or is a snake? All right, so let's write out probability poison or snake. And we're going to have to use our general addition rule. That's going to be the probability that it's poisonous plus probability that it's a snake minus the probability that it's poison and a snake. All right, so let's find out, first of all, what our denominator is going to be. So it looks like 9 poisonous snakes plus 7 non-poisonous plus 8 poisonous spiders plus 5. So there are 29. So n in this case is 29. So that's going to be my denominator each time. All right. So probability of poisonous. How many poisonous? So there's 9 plus the 8, it looks like to me. How many snakes are there? That's going to be the 9 plus the 7 over 29. Now, do you see I have a 9 in both of those? That's the overlap that I'm talking about. So what we need to do is subtract off any poisonous snakes because we've counted them 2 times. And this should give us our total. (17) plus 16 minus 9. That's giving me 24 out of 29, which is about their point. They say nearest hundredth, that's going to be 8, 3. So about an 83% chance that she's going to randomly pull out either a snake or something poisonous. All right, that is going to do it for this video. Thank you for coming.